The universe is already dying, not dramatically, not with an explosion that tears through space and erases everything at once, but slowly, silently, and absolutely inevitably. From the first instant after the Big Bang, when matter and energy burst from nothing and began forming all that exists, a relentless process was set in motion. That process has a name, entropy, and it is fundamentally the reason the universe has an expiration date. This is not speculative theory, nor philosophical hypothesis. It is a direct consequence of the laws of thermodynamics, confirmed in every laboratory ever built and observable in every phenomenon you have witnessed in life. Entropy describes the tendency of physical systems to evolve from order into chaos. A hot cup of coffee cools because heat flows naturally from warmer to cooler, spreading energy ever more uniformly through its surroundings. A brilliant star consumes its nuclear fuel and gradually fades. A galaxy that seems to spin in perfect harmony slowly disperses across eons on a cosmic scale. This means all usable energy in the universe. All light, all heat, every temperature difference that allows any physical process to occur is being continuously spent and redistributed ever more uniformly across expanding space. And when that distribution becomes absolute, when no temperature difference remains between any 2 points in the cosmos, nothing more can happen. No process, no motion, no change of any kind. The universe ends not with a scream, but with a whisper no one will remain to hear. Before going further, we must calibrate the timescale we are contemplating. The universe is roughly 13.8 billion years old. That seems like an eternity from a human perspective, but in cosmic terms, we are living in its infancy. The stars we know, those that blaze across the night sky, that warmed planets and forged the elements composing every atom of your body, represent a relatively brief chapter in cosmic history. Imagine all of time compressed into a single calendar year. On that scale, the 13.8 billion years already elapsed would fill only the first days of January. The end-state scenarios physics predicts would unfold at some point trillions upon trillions of years in the future. Periods so vast that numbers lose all intuitive meaning and must be written in scientific notation with exponents that cannot fit on a single line of text. In the late 1990s, astronomers studying distant supernovae discovered something no one had anticipated. These stellar explosions, used as reliable cosmic distance markers, were farther away than any physical model had predicted. The conclusion was inescapable. The universe's expansion was not slowing under gravity, as expected since the last century. It was accelerating. Something invisible, with no known mass, no charge, no name, was pushing the cosmos outward against the gravitational pull of all existing matter. This something was called dark energy, and it accounts for roughly 68% of all the energy in the universe. Its discovery permanently reshaped the map of cosmic destiny, revealing that expansion has no natural break and that the fate of the cosmos depends critically on a force we still do not fully understand. The universe may die in absolute cold, in a state known as heat death. Expansion perpetuates forever. Stars extinguish one by one. Everything cools to temperatures near absolute zero, and nothing ever happens again. It may tear itself into ever smaller fragments if dark energy surges beyond a critical threshold, destroying first the galactic clusters, then individual galaxies, then stellar systems, then planets, then atoms themselves, in an event called the Big Rip. or it may collapse back into a state of extreme density and temperature, the Big Crunch. If gravity prevails over expansion in ways current models have yet to predict. Each scenario is grounded in concrete observational data, and the choice between them depends on measurements that next-generation telescopes are making right now, at this very moment. The hardest of these possibilities to imagine is not the Big Rip or the Big Crunch, but heat death, precisely because it involves no violence, no drama, no explosion, only the silent continuation of what is already happening, carried to a conclusion that eliminates any possibility of future events. The universe's average temperature today is roughly 2.7 Kelvin, nearly 270 degrees below 0 Celsius. In heat death, that temperature converges toward an even closer approach to absolute zero, spread uniformly across a dark and empty cosmos. Nothing left to measure, no observer to record, no process to distinguish one instant from the next. Time would still exist, mathematically, but nothing could ever happen within it. And it is precisely here that the most radical question modern physics has tried to answer emerges. What comes after? Is there an after when the end is the end of all matter, all energy, all space, and all time as we know them? This question is not science fiction. It is an active field of theoretical cosmology where formal calculations and observational inferences are producing answers that defy all intuition. In the chapters ahead, we will traverse the eons of future time, watch the last stars fade, witness the final black holes evaporate in absolute silence, and then reach the most extreme frontier physics has ever known. Prepare to go beyond the end of the universe. Of all the scenarios physics offers for the end of the universe, none is more supported by current data than heat death. Measurements of the cosmic expansion rate and dark energy density consistently point to a universe that will keep expanding indefinitely, with no force capable of slowing or reversing that motion. If this trend holds, and all available evidence suggests it will, the universe will not end in fire. It will end in ice, in a silence so profound that the very word silence becomes inadequate, because silence implies a backdrop against which nothing resonates, and in the final state of heat death, even that backdrop will cease to exist. The path to that final state is long, and the universe will not arrive there all at once. Physicists have identified distinct eras along the cosmos's future timeline. The current age, known as the stellar era, is the one we inhabit, billions of galaxies each, holding hundreds of billions of stars, fusing hydrogen into helium, producing light and heat, feeding planetary systems, and making any form of chemical complexity possible. This era will continue for a long time, but it has a deadline. The universe has held a finite supply of hydrogen since the Big Bang, and stars have been consuming that supply without pause. The smallest and most efficient, the red dwarfs, at around 8 to 10% of the sun's mass, can burn for up to 100 trillion years. To grasp that scale, if 1 centimeter represented the current age of the universe, 100 trillion years would span a distance of over 7,000 kilometers. If instead, dark energy does not remain constant but grows stronger over time, the universe follows a very different and far more violent path. The Big Rip. In this scenario, the cosmic repulsive force gradually intensifies until it overpowers every other known force, one by one. First, vast galaxy clusters are torn apart, their gravity too weak to hold. Then, individual galaxies dissolve. Then, stellar systems disintegrate. Then, planets are ripped from their orbits. As the end draws near, The force of expansion overcomes even the interactions binding atoms together, and in the final instant, subatomic particles themselves are torn into fragments that will never recombine. The universe unravels down to the most fundamental level of matter. Models best fitting current observations suggest the Big Rip would occur around 20 billion years from now if dark energy intensifies at the required rate. That span is less than the age that separates us from the Big Bang. About 1 billion years before the end, galaxies begin to irreversibly drift apart. 60 million years before, the Milky Way dissolves. 3 months before the end, the solar system falls apart. 30 minutes before, Earth is destroyed. And in the final seconds, the atoms composing whatever remains are torn from within. The sequence is precise, relentless, and from a purely physical standpoint, remarkably elegant in its logic, each structure destroyed in exact order, determined by the strength of the forces that once held it together. The third great scenario, the Big Crunch, assumes that gravity, at some future point beyond current models, overcomes accelerating expansion and reverses the motion of all galaxies, drawing them inexorably toward one another. Over billions of years, the universe would progressively shrink, temperatures and densities would surge, and the cosmos would be compressed back into a state of extreme heat and near infinite density. Paradoxically, some cosmological models suggest a Big Crunch could spark a new Big Bang, an eternal cycle of expansion, collapse, and rebirth that would make the universe we know merely one link in an endless chain of successive cosmos, each inheriting something from the one before. Current data, however, does not favor the Big Crunch. The accelerating expansion, confirmed by multiple independent observations over recent decades, points to heat death as the most likely fate. But most likely does not mean certain. The physics of dark energy remains deeply misunderstood, and more sophisticated models continue to be tested against new measurements from cutting-edge space telescopes. The universe has not yet revealed with certainty which of its endings awaits us. What we know is that we exist within one of these scripts, and each leads to the same starting point for the next great question. What happens on the long road to the end, era by era, extinction by extinction? If heat death is the universe's fate, the path toward it is a story of gradual extinctions and progressive silences, one that physics can narrate with astonishing precision. It is not a sudden blackout. It is a slow dimming era by era, transforming the brilliant, restless cosmos we know into something ever quieter, colder, emptier. To understand what happens after the universe ends, we must first understand what happens on the long road that precedes that end, a road spanning spans of time that demand an entirely new language to describe with any honesty. We live today in the stellar era, the age when stars form, burn, and die, feeding with their light and elements, the process that made chemical complexity and life possible. This era began relatively soon after the Big Bang and will endure for a long time still. But it has a clear limit. The gas available to form new stars is finite, and star formation rates have been declining for billions of years. The universe forged more stars in the past than it does now, and in the future it will forge fewer still. The last stars to form will be red dwarfs, tiny and extraordinarily efficient, burning so slowly they can shine for up to 100 trillion years before exhausting their fuel, but even they eventually go dark. When the last red dwarf exhausts its hydrogen and becomes a white dwarf, cooling in silence, what cosmologists call the degenerate era begins. The universe of that age is inhabited mainly by white dwarfs, the glowing remnant cores of long-dead stars, along with neutron stars and black holes, relics of the most massive stars. The remaining light grows ever fainter. The space between these compact objects grows ever vaster. The temperature of the universe keeps falling. Over immensely long periods, white dwarfs cool until they become black dwarfs, cold, dense, and utterly dark objects that emit no detectable radiation. The universe does not explode at this stage. It simply stops shining, object by object, until no light travels through space at all. Running in parallel with this darkening is an even slower process, the possible decay of the proton. Theoretical physics suggests, though not yet observationally confirmed, that protons themselves, like the fundamental building blocks of atomic nuclei, may be unstable across enormous timescales. If protons decay, it means all baryonic matter in the universe, including white dwarfs and neutron stars, gradually disintegrates into lighter particles. In this scenario, the universe would lose even these last strongholds of dense structure. What remains would be predominantly black holes and elementary particles drifting through an ever emptier, ever colder, ever more silent void. The black hole era begins when black holes become the only complex objects left in the cosmos. They exist across a vast range of masses, from stellar black holes of a few dozen solar masses to the supermassive monsters at the hearts of galaxies, with masses of tens of billions of suns, yet all of them share the same fate. An extraordinarily slow evaporation, a process physics predicted theoretically, but one never directly observed, precisely because it unfolds across timescales far exceeding the current age of the universe. The black hole is not eternal. It slowly radiates energy, loses mass across eons, and inevitably vanishes. What makes the black hole era so difficult to grasp is not the physics, it is the scale. A stellar mass black hole would take roughly 2, followed by 67 zeros in years, to fully evaporate. A supermassive black hole, with tens of billions of solar masses, it would take a number with roughly 100 zeros in years. For any reference, the current age of the universe has just 11 digits. We are speaking of numbers with no analog in any human experience, in no geological or astronomical scale we have ever used. And yet, physics tells us these black holes will evaporate. Time in this context is the only force that matters, and time has all of them. At the end of the black hole era, when the last supermassive black hole completes its slow evaporation, the universe reaches a state with no adequate name in any human language. Because no human language was built to describe the total absence of events, what exists in that moment is only expanding space, impossibly dilute, and a faint bath of elementary particles with near-zero energy. Drifting without direction, without destination, with nothing meaningful to interact with. The universe's temperature at that point is so close to absolute zero that the difference between it and zero itself is unmeasurable by any conceivable instrument. This is thermal death. This is maximum entropy. The mechanism that evaporates black holes works as follows. According to quantum mechanics, apparently empty space is not truly empty. Pairs of particles and antiparticles spontaneously emerge from the quantum vacuum everywhere and at all times. They exist briefly, then annihilate each other without a trace. Near the event horizon of a black hole, this process has a peculiar consequence. One particle from each pair can fall into the black hole while the other escapes into outer space. From the perspective of an external observer, it seems the black hole emitted a particle and paid for it with a loss of energy and therefore of mass. The black hole grows thinner, slowly, glacially, across spans of time that defy all comparison. It sheds mass until the final moment, when the last grams are released in a small flash of energy, the last observable event of an object that outlasted every other thing that ever existed in the cosmos, combined. The final flash of a black hole is a moment of profound paradox. For an instant, something happens where eternities had passed with nothing. A minuscule quantity of energy is released into empty space, and then silence returns. If some theoretical observer were there to witness that instant, they would see a fleeting point of light emerging from absolute darkness, followed by an immediate return to the total absence of events. The universe emitted its last signal. After that, no energetic process remains. No temperature gradient left to exploit. No imbalance of any kind. Entropy reached its maximum, and the universe arrived at the state the second law of thermodynamics always pointed to as its inevitable destiny. In this state, time continues to exist mathematically. The equations of physics persist, valid in principle, and the universe has not stopped in any technical sense. But time without events is indistinguishable from time without time. If nothing happens in 1 billion years, that is no different in practice from nothing happening in 1 trillion. No clock marks the difference, because every process that could serve as a clock has ceased. The question of how much time has passed since the last event becomes unanswerable and more profoundly, physically meaningless. The universe in heat death does not exist within time the way the universe we know does. It dwells in something language has no name for, no precise way to describe. What is staggering about this state is not the horror it might first appear to be. It is the precision with which physics can describe something so radically different from anything that exists now. We are not speculating about metaphors or vague possibilities. We are describing the logical consequence of the laws governing every particle, every force, every interaction in the cosmos. The second law of thermodynamics is not a tendency, it is an absolute rule with no known exception. And its inevitable conclusion, carried to the very end of time, is this state of perfect uniformity where no process can ever occur again. Physics tells us, with all the precision its instruments allow, what happens when the universe's story reaches its final chapter. But heat death is truly the end. The absolute silence, the ultimate destination. The last page of the last story, begun 13.8 billion years ago in a burst of energy, ending in an inaudible whisper across an empty cosmos. Or is there, hidden within the very laws that produced this end, something that can emerge beyond it? That question, the most radical of this entire journey, is exactly what the next chapter will answer. And the answer is the most astonishing of this entire story. The quantum vacuum is one of the most unsettling ideas in modern physics. Even at maximum entropy, even when the universe has reached the deepest silence the laws of thermodynamics allow, space is not truly empty in any absolute sense. It is permeated by quantum fluctuations, tiny spontaneous variations in the energy fields that exist at every point in the cosmos. These fluctuations require no external energy to occur. They emerge from the fundamental uncertainties quantum mechanics imposes on any physical system. And in a universe that exists for a sufficiently long time, even these infinitesimal events carry consequences that the logic of probability makes inevitable. The reasoning is this: if a universe in heat death persists long enough, and here long enough means spans whose digit count exceeds anything this narration could contain, then quantum probabilities, however small, are not zero. And across indefinitely long time, non-zero probabilities become statistical certainties. This means that at some indeterminate but real point in the cosmic future, a quantum fluctuation could spontaneously produce a localized concentration of energy in space, an event that, under the right conditions, could trigger a new period of inflationary expansion. In other words, a new Big Bang, a new universe born from the silence of a dead one. Not through any external force, but as a direct consequence of the laws of physics applied across a timescale long enough for the improbable to become inevitable. This scenario has a specific version that forces physics to confront one of the most unsettling ideas it has ever produced. If random fluctuations can create any configuration of matter and energy given sufficient time, they can create very simple configurations, a particle, an atom, but also, in principle, extraordinarily complex ones. Given truly unlimited time, the probability that a quantum fluctuation accidentally assembles a conscious mind, a complete observer, with memories and perceptions arising from the vacuum by pure chance, is infinitesimal, but it is not zero. These hypothetical observers have been called Boltzmann brains. Whether they are more likely to exist than minds arising from biological evolution in young universes is one of the most serious and debated problems in modern cosmology, because if they dominate the landscape of possible observers, it profoundly changes how we interpret our own existence. Beyond quantum fluctuations, there exists an even more ambitious scenario, derived from the theory of cosmic inflation, the eternal multiverse. In this model, inflation, the period of ultra-rapid expansion occurring in the first instance after the Big Bang, never ends completely across all of space. Different regions of inflationary space stop inflating at different moments, and each region that ceases becomes a universe with its own physical constants, its own properties, its own history. In this model, our universe would be a bubble in an infinite ocean of other bubbles, each with potentially different physical laws, each ignited by an event of inflation halting in a different region of eternal space. Our universe would not be unique, one among countless others, rising and ending, while the greater inflationary process continues indefinitely, generating new cosmos in regions of space we will never reach. Cyclic cosmology proposes yet another possibility, that our universe is one link in a chain of universes succeeding one another. In a great collapse followed by a new Big Bang, called the Big Bounce, each cycle generates a universe whose initial conditions are shaped by the physics of the cycle before. The universe would have no absolute beginning or end, but would be an oscillating process that perpetuates itself, transmitting something of itself to the next cosmos. Some more recent versions of this model propose that certain physical information from previous cycles may persist encoded within the structure of the nascent universe. If this idea is correct, then the Big Bang that created everything may have been preceded by another cosmos, and the end of our universe may be the beginning of something we have no language yet to name. Which brings us back to where we began, and to perhaps the most profound reflection this journey beyond the end of the universe has revealed. You exist now, in this moment, during the cosmic infancy of the universe. The atoms that form your body were forged inside stars that exploded before the sun ever existed. The energy firing your neurons comes from a star that has burned for 4.5 billion years and still has billions more ahead. You are, literally, the universe observing itself, a temporary configuration of matter and energy complex enough to contemplate its own origin and its own fate. And the question that remains after everything we have explored here is not whether the universe ends. The question is what it means to exist briefly within a story so long and so extraordinary. If a new universe could be born from the silence of ours, be born from a quantum fluctuation in a cosmos that had exhausted every star, every black hole, every structure, do you think it could produce something as improbable as consciousness again? Leave your answer in the comments. If this journey changed how you see the night sky, share it with someone who deserves to look up with new eyes, and turn on notifications so you don't miss what comes next. There is still much of the cosmos we have yet to reveal.